So, we will go on to another problem of a slightly different kind. Here we have a problem which says there is a tank A, which is here, and a piston cylinder arrangement B, which is shown here. They are connected through pipes as shown. The piston, there is a piston over here which can move in the cylinder. The piston is frictionless. Sorry. Tank A contains nitrogen. Okay, the gas here is nitrogen. The pressure is 300 kilopascals. And its volume, I am going to call that as V1, is given as 0.4 meter cube. So, it requires 150 kilopascal to lift the piston. So, this piston will only move up if the pressure here is at least 150 kilopascal. There is a valve in between. So, this is the general symbol of a valve. As the connecting valve opens, nitrogen flows into the piston cylinder arrangement B. So, when we open this valve, nitrogen will flow like this, and it will try to push this piston up because the pressure here is higher than the pressure it requires from pushing this up. And so, what it says is, as the connecting valve is opened, nitrogen flows into this arrangement and attains a steady state after some time. So, what we expect is, if I open this valve slowly, then nitrogen will slowly flow in this pipe. It will try to push this piston up. Pressure here is 300 kilopascal. This will move up if the pressure is more than 150. So, right now it is 300, it is more than 150. So, this will move up. As this keeps moving up, the volume increases because it is going to, finally the piston is going to come somewhere like, let us say here. So, this volume is also occupied by nitrogen from this. So, the pressure in this tank will keep coming down, and at some point of time the pressure here will become 150, the pressure here is also 150, it cannot push this piston anymore, and we expect that at that point of time things will become stationary. So, we will reach a steady state where this has moved there and it has stopped. We are asked to find out the final pressure and work interaction for nitrogen if the initial and final states are related by PV is equal to constant, where P and V represent the pressure and volume and C represents a constant. So, we are going to look at this mass of nitrogen. This is initially our system. Finally, our system is this plus whatever is the nitrogen here, because what we see is initially all the mass is here. So, what we are going to assume is that there is no mass of nitrogen in the pipes. So, we are going to assume the pipes are so small that we do not have to worry about whatever is the mass of nitrogen is sitting inside the pipes. Initially it is 0, finally we are going to ignore it. Initially all the mass was concentrated in tank A. So, our system is the mass of nitrogen in tank A. After the valve is opened, some of that mass goes and sits here. So, our system is still all the mass of nitrogen which was there, but now some of that volume is here, some of that volume is there. So, the same mass has just been split into two volumes, but we are going to do a system analysis. So, the mass is constant. So, mass is whatever was there initially here, which is finally partially here and partially here. So, that is essentially how we are going to deal with this. There may be some heat interactions here, we do not know what they are. So, we are not going to worry about that. So, what we can see is we have a valve here. So, we have discussed earlier that we can deal with processes provided they are quasi-static. If they are near equilibrium, they happen slowly. So, if we did not have a valve here and we connected these two tanks, all of this nitrogen will suddenly rush from here and go there. So, the idea of a valve is to make the process slow. So, we are going to assume that the process is slow and it is quasi-static. We are also going to assume there are no losses because of the valve. For the time being, we are going to assume these. So, let us see what is known. We know that the mass is constant. So, we are going to do system analysis, and we have identified the system, which is the mass in tank A initially and the mass in tank A plus B finally, both of them are the same. So, that is our system. The substance is nitrogen. Initial pressure P1 is given as 300 kilopascal. Initial volume is 0.4 meter cube. So, we know the initial state. We do not know the mass, but we can find out other things which we need. What we know is that this will only move if the pressure is 150 kilopascal. So, we slowly let gas through this valve here. The pressure in this pipe will build up until it reaches 150, there is nothing moving. Once it reaches 150, this will start to move up. It will continue to move. While it is moving slowly, the pressure will remain 150. It will stop to move when the pressure in the tank becomes 150. So, what we know is that the final pressure in this as well as this will be the same, and that final pressure is also 150 kilopascal, and all through the process, while this is moving, it is near equilibrium, it is quasi-static. Through the entire process, the pressure here is 150 kilopascal. That is also something which we know. So, what we know is that this process by which this piston is moved up, whenever it is moving, the pressure below it is 150 kilopascal, which means that it undergoes a constant pressure process. In B, such that this piston is moved up. So, the piston is lifted up in a constant pressure process. So, that is also something we know. We have a relation for the initial and final states given as PV equal to constant. So, we are going to use that. So, for the initial and the final states, we have PV equal to constant between the initial and final states, or just at initial and final states, this is true. So, P1 V1 is equal to P2 V2. I know P1, it is, if I remember correctly, 300 kilopascal. I know V1, it's 0.4 or was it 0.6, it's 0.4 meter cube. I know P2, it's 150 kilopascal. I do not know V2, but I can find out V2 from this. So, this is 2, so that is 0.8 meter cube. So, I know the value now of V1 and I also know the value of V2. So, I know the initial state, I also know the final state. What I want to know now, the final pressure which I have already found, 150 kilopascal, because it is a constant pressure process. I want to find out the work interaction for nitrogen. So, now what this nitrogen is doing work on is it is doing work on the atmosphere, because the piston is moving against the atmosphere. It is doing work on the piston because it is lifting the piston. So, it is doing work on the piston as well as the atmosphere. But the pressure of the nitrogen here is always 150 kilopascal. So, I can find out the work done, which is essentially the work done in a constant pressure process. So, the work would be given as integral of P dV from 1 to 2. In this process, the pressure is always constant. So, I can take pressure outside. So, this is like some integral of some constant times dV, which is that constant into integral dV. This constant of course is the pressure. So, this is 150 times integral of dV is V2 minus V1. V2 is 0.8 meter cube, this is in kilopascals, this is in meter cube. This comes out to be 60 joules. That is not quite true, because I have missed out the fact that it is a kilopascal here. So, this is kilopascal into meter cube, which is kilojoule. So, the work interaction for the nitrogen gas is essentially 60 kilojoules. This question does not ask for anything beyond this, it does not also give any more information beyond this, but what we would normally expect. So, we had this tank here, we had the valve, and we had the piston which was moving. So, if the pressure here was known, so let us assume for a moment that the pressure here was 100 kilopascal, then what we would see is that in moving out, the work done for the atmosphere, okay, the work interaction for the atmosphere would be also given as integral 1 to 2 p dV, where P is the atmospheric pressure outside, which is constant. So, this would be essentially so if the atmospheric pressure was 100 kilopascal, we do not know it in this particular problem, but supposing it was, this information was given, and we have dV is V2 minus V1, which is essentially 0.8 minus 0.4, which is 0.4 meter cube. Then if we multiply these two, so we have 100 kilopascals and we have 0.4 meter cube. So, we would get this as 40 kilojoule. So, we would get the work interaction of the atmosphere as 40 kilojoules, and whatever is the difference. So, we have the condition that all sum of all the work should be 0. So, interaction of work for nitrogen plus this is minus 40 kilojoule, because as far as the atmosphere is concerned, the volume of the atmosphere is reducing because the system is expanding against the atmosphere. So, if I was to take the atmosphere as whatever is the remaining, so that is being reduced. So, this would be given as dV, where dV in this case I have taken V2 as the final volume of the other system, of this system. Okay. So, the change in the case of the atmosphere would be the opposite. Okay. So, it would be minus 40. So, I would have this condition: work interaction for the nitrogen plus work interaction for the atmosphere plus work interaction for the piston should be 0. So, which means that I can find out also this value if I knew this. So, the work interaction for the piston in this case, assuming atmospheric pressure as 100 kilopascal, would be minus 20 kilojoule, which is to say that the piston is being lifted up against gravitational force. And again, if I so I do not know how much is the distance it is moved by, because I do not know the cross sectional area of this piston and cylinder. If I knew that, then I could also, this would be equal to mg into h with the appropriate sign, so minus over here. So, if I knew height, I could find out the mass of the piston, or if I knew the mass of the piston, I could find out the height by which it is moved, and so on. I could also do that. So, what we see is that of course, the sum of all of the work should be 0. In this case, there is a constant pressure process which is lifting the piston up. There is work done against the atmosphere, there is work done against the piston in lifting it, and all of that is done by the nitrogen over here.